So moving forward, it's really hard for me to go back and like, if you didn't get full points on one of the mastery thingies that I put in MATLAB. If you didn't get full points and then you go and do that assignment like later, I need you to upload a screenshot of your new score into the assignment link. Because now there's so many that it's just too hard for me to go back and check to see if you did it. But if you did it, put your updated screenshot into the MATLAB Schoology link for that lesson. Now, we're also to a point where you might actually have some missing mastery objectives or like missing work from algebra. Make sure you pay attention to what we're doing like today. Like today is going to be lesson 10, which since you're all here, I'm holding you all accountable to lesson 10. Sometimes when you're absent, I'll excuse you from like the MATLAB part of it, not necessarily the algebra, like you still have work to make up in algebra, but I try not to like overwhelm you. Okay, so I usually just do it based on whatever days you're here. So make sure you pay attention to that. Don't necessarily work backwards unless you finish the stuff from today early or something like that. So today we did average rate of change, which we've done before. So when you hear that phrase, you should automatically think of a certain formula. What is the formula for average rate of change? Okay, great. So if you don't know that, or maybe you haven't had algebra yet today, maybe write that down. Average rate of change is this formula. It's something that we expect you to remember because we do it so often. So if you don't know it already, start memorizing it. But basically, it's the change in your outputs divided by the change in your inputs. So to use this, you would need like two coordinates. You can get the coordinates from a table, from a graph, from a description. Say that my coordinates are this. I would make one of them x1, y1, the other coordinate x2, y2, and then I plug it into this formula. I never skip the labeling step because when people do, they make mistakes. So I never skip that step. However, I labeled it is how I put it into the formula. So what did I say my y2 is? So it's going to be 6 minus, what did I say my y1 is? Over, what did I say x2 is? Minus my x1, which is, and then you simplify, which really you can put this whole thing in Desmos if you know how to put it in the right way. If you're putting it in a normal calculator, just make sure you put parentheses around the numerator and then around the denominator. But sometimes they're easy to work out by hand too. 6 minus 4 is 2. 5 minus 3 is 2. What is 2 over 2? Simplify 2. So my average rate of change from this point to that point is 1. And since it's positive, that means it increased. If my average rate of change is negative, then it would decrease. And now that we're no longer just looking at linear functions, so not just straight lines anymore, you really have to pay attention to what time they specify. So if they say they want to know from when x is 3 to when x is 5, then make sure you use the correct coordinates. But I think average rate of change is easy, but usually on a test, they make you type in your answer. And because of that reason alone, students get it wrong. I don't know, they stress out. It's really just this. So pay attention to what time they want you to look at. Remember the formula, plug it in and solve. Don't round unless they tell you what they want you to round. So questions on that? Okay, we'll even do another example just in case, but you're looking on the wrong slides. But your 80% or higher like mastery objective today is for lesson 10. So do try that first. That's the one that I think most people will ask about today, but you're welcome to ask about any practice anytime. You're welcome to ask about the math lib anytime. So like if you have a really low grade on that and you want to prioritize that, by all means. But for the mastery objective today, it's this practice. So any questions on that? Okay. I'm gonna pull up another example just because not everyone had algebra or yet. So I will show you like an example. So Nelson took a summer job for 5 weeks where he received a weekly salary plus tip. His take-home pay is recorded in the table. What's the average rate of change in his weekly take-home pay over the 5 weeks of his job? So it's wanting to know from what time period to what time period. So the question I'm asking right now is from what time period to what time period do they want us to calculate the average rate of change for? From week 1 to week 5, because it said over the 5 weeks. On another problem, it might say, what's the average rate of change from week 3 to week 5? Or from week 1 to week 4. You just gotta read it. Since it said over the 5 weeks, that implies from week 1 to week 5. So then that means this is my first coordinate. Here's my second coordinate that I need. Make one of them x1, y1. The other one x2, y2. And plug it into that formula that I told you you need to memorize, but it's okay to look at it when you're practicing. So the way that I labeled it, what's my y2? 80. What's my y1? What's my x2? And what's my x1? What's 80 minus 60? What's 5 minus 1? What's 20 divided by 4? 5. It happens to not be a decimal, but it could be. And that's it. So what that means is on average over those 5 weeks, his salary increased because it was positive by $5 a week. Now, is that necessarily true throughout? No, like here from here it's true. From 72 to 75, it only increased by 3. But on average, that was the rate of change. Just depends where you look. So there's the example. Again, the practice is lesson 10. Feel free to ask questions as well or about any other practice. I'll check in with you later for any questions.
So feel free to follow along or continue working by yourself, but this is being recorded. It'll be posted in the slides. I really do want you to try it first, before you just get the answers. So you can see where you need to focus more. But number 5 from the lesson 10 practice, a moth population is modeled by this equation where W is the number of weeks since the population was first measured. So looking at how this equation is set up, is that a linear or an exponential function? It's exponential. So that tells you to refer back to our very standard exponential function equation where we picked apart what each part represents. So y would just be your output. A is what? Good. Starting amount, initial amount. B stands for what?
common factor, whatever you're having to multiply by each time to get to the next number. And then X is usually what? Time. Which is usually what you input so that you can get your output. So knowing that, that should help us answer these. So what was the moth population when it was first measured then? 500,000, because it's the number that's not attached to the exponent. So that has to be my initial amount. I wouldn't put the comma. Okay, just because on like your state testing, I feel like they don't do that. And in general, like when you put a number in the calculator, you don't put the comma. So I would just not. It shouldn't matter if you did. It won't mark it wrong because we set it up to where it takes both answers, but I just wouldn't put it moving forward. Then it says, what was the moth population after 1 week? So I need to go back, reread what is the time being measured in? Because if it was measured in like days, and I wanted to know after 1 week, then my exponent would be 7. If I wanted it in like a month, and it just, so like if my exponent was measured in a month and it wanted after a week, then my exponent would have to be 0.5. So read how they're defining the exponent. It stands for weeks. So then if I want to find it for after 1 week, what's my exponent going to be? 1. So then you'll put that in your calculator where the exponent is 1, which anything to the power of 1 is just that number, right? So it ends up being 500,000 times 1/2, which was half of 500,000. Okay, good. So that's what should go here. What was it about 1.5 weeks later? So then now my exponent is going to be 1.5. That math I cannot do in my head, so I'm actually going to pull up the calculator now. And it really stinks to not like know how to use the calculator. I know I failed a few tests in chemistry just because I didn't know how to press like a special button for negative numbers. So like, please, if you're not getting the same answers that I am, and you're using the calculator that you asked. But for that one, it should look like this before you press enter. And this is my answer. I wanted it rounded to the nearest 1,000. So 1,000, not thousandths with the TH. 1,000 would be this spot. Okay, not thousandths with the TH. 1,000. So that's my thousandth place. Anywhere you're supposed to round to, I would like, at least in my head, visualize that I'm underlining it. Look to the right. Since the number to the right of where I need to round to is a 7, that means I need to round up. So what I need to enter is going to be this. That's rounded to the 1,000 place, not with the TH. Okay, so let me go back 177,000. And then use technology to graph the population and find out when it falls below 10,000. So when it says use graphing technology, to do that, I would make the exponent an X, because it doesn't read T's. I'd make it an X so that I could see it on my screen, and I can't see it right now, so I might have to adjust the window or zoom out. Let me go to my computer to see from there.
And then we're gonna estimate for when it falls below 10,000 and we're rounding to the nearest 10. Okay. Yeah, the window is not working really well, so I'm gonna adjust it. So to adjust the window, do the wrench. And since we want to know for when it falls under 10,000, I'm gonna make my Y's go up maybe like 10,100 or something like that. Okay, so I hit the wrench, I adjusted the Y's to be up to that point. And I don't know what my X's are right now, so I'm gonna have to like see. Okay, maybe I'll adjust the X's. I don't really know what to adjust it to because I don't know what my answer is gonna be. But do you see 10,000 on the Y? You see how I can click and drag up to the 10,000? We want to know when it falls below 10,000. So I'm going to try to get as close to 10,000 as possible. I think I'll adjust this to something in a second. Okay. I'll adjust my x-axis to go to like 1 through 5. Or maybe even like a little above that. So I can see it better. So like 0 through 7, I adjusted the x-axis so I could see it better. We want to know when it falls like below 10,000. So I'm going to click and drag, might have to like zoom in. Okay, I feel like that's as close as I'm going to get. It's a near 5.6. So I'm going to go back to my key and I'll check the answers. It says rounded to the nearest 10th, so the 10th would be about 5.6. Let me type in all my answers and see if I'm right. Okay, it looks like it's not wanting my last answer, which they said it's 5.5. I'll make it accept 5.6 as well. So hang on. But automatically it's marking 5.5. I feel like maybe I just might have to get closer. But I'm seeing it as near 5.6. So okay, but any questions on that? Yes, let me pause this real quick. All right. I'll make it accept both. But from what I saw, it looked like it should be 5.6, but I'll check the key. I'll still make it accept 5.6 because to me, that's what it looks like, but we'll see. Anyway, number 4 on the same practice, the function f gives the number of copies of a book has sold W weeks after it was published. This equation defines the function. Select all domains for which the average rate of change could be a good measure for the number of books sold. So domain is referring to what? All the what in a function is my domain? The x's. All right, so remember Dr. XY is an easy way to remember it. Domain is referring to all the x's or all the inputs. In this case, where my x would normally go is here. It's standing for weeks. So it's asking for what number of weeks would the average rate of change be a good measure for the number of books sold. So let me take you back to the notes, and I know not all of you have had the lesson today, but I think the notes has a good example. Here's like, the dots are what we were given. The lines are average rates of change from like particular time frames. So like from the beginning to the end, from like the beginning to about the middle, and from the beginning to like the first 3 weeks.
This visually tells you that like, if you're looking at a smaller time frame, you're gonna have a better estimate for that average rate of change. If you're looking at a bigger time frame, because exponential functions change at such a fast rate, it's not necessarily gonna be a good fit. You see what I'm saying? So then, using that knowledge, I'm gonna go back to this and just pick out like my smallest time frames. So this goes from 0 to 2. I'd say that's like a difference of like 3, like 0, 1, 2. 0 to 7 is like across 8. 5 to 7 is 3. 5 to 10 is 6. And 0 to 10 is 11. So the smaller time frames have better estimates because it changes less within those time frames. So what should my two answers be? Which ones would have the smallest time frame? On my screen, it's A and C. It can be shuffled on yours. But I would agree, probably just those two. I would pick, we'll see if the answer is right. But the smaller time frame that you're looking at, like smaller amount of weeks, whatever the situation is that you're looking at, the better the estimate will be than if you looked like from 0 to 10. It'll be a large difference there. So let's show answers. And that's right. So to answer these, which one would be a good measure? You pick like the smallest time differences. Why would you make B? Because B is going from 0 to 7. That's like even if, and I know this is a different situation. Because it's a hard thing. Correct. So I know this is a different situation, but it'll probably look really similar. If I go from 0 to 7, do you think that this line touches a lot of the points? So then that's less of a good fit. Because they're more spread apart. Okay, questions on that one? Questions on any others? Choose faster, but I mean, I have you both later, so just whatever question you have, ask me later. Number 3 was asked about. So, function F models the population in thousands of a city 2 years after 1930. The average rate of change. Okay, can you guys just chill for a second? So it's not so loud in here. But the average rate of change from t = 0 to t = 70 is approximately 14,000 people per year. Is this value a good way to describe the population change of the city over that time period? So look at your graph that you're given. From t = 0 to t = 70, which I need to scroll up a bit more to even see that point. If I were to draw a line to it, because that's what my average rate of change would be. Basically more of a linear thing, but if I were to draw a line to it, would you say that it touches most of the dots? So I would say that it's not a good measure because it really doesn't touch really any of the points. So I would probably lean toward the nose, and the reasons, let's read them. The average rate of change was much greater than 14,000 people per year. Or the average rate of change was much less than 14,000 per year. Approaching the year 2000, which was 70 years after 1930, the average rate of change was much greater than 14,000 per year. I would lean towards this one. Because as we get closer to like the end of the time frame, the change is actually going to be wider, I guess you could say, than when you go to like the beginning. And that is correct. All right, so if you still have questions, you know, you can email me, you can ask me about it later. So make sure you're reaching that 80% of time.